All right, AP Classroom. So this is Unit 7, Rotational Dynamics. Ooh, looks like the first three questions are all linked together here. Group of students must conduct an experiment to determine how the location of an applied force on a classroom door affects the rotational motion of that door. Rotational inertia of the door about its hinges is known. Okay, rotational inertia. That is something to do with mr squared, right? How massive is it, but also where's location at mass relative to the hinges in this case, right? So that's like a known value. If they wanted you to do a calculation, they might give you some numerical value. With what units? Guys, what's the unit for rotational inertia? Hint, mr squared as variables. What's the units for that? How do you measure mass? Kilograms? And radial size you can measure in meters. So that would be kilogram meter squared, wouldn't it? Kilogram meter squared, right? Right. The initial angular velocity of the door is 0, so it starts at rest. Show you one more thing on angular momentum. Let me switch my screen over here. All right. So you guys remember this rotational inertia? So for a single point, it's mr squared. A ring rotating about the central axis is just a series of points, so it's also mr squared. But all these other really shapes, well, you might have more mass that's distributed closer to that rotation axis, so it'd be less than mr squared. Like a solid cylinder rotating, it's like 1/2 that. Hey, could a door be basically this right here? A door? Because here's the door hinge, here's the door knob, right? What if you just had a bunch of sticks all stacked vertical? It would just be that, wouldn't it? Like if you were given the mass of the door and the width of the door, that's all you would need, right? You could just do that. Right? All right, so that's a side thought. You would not be expected to memorize that or know that, but just to make a connection there, that would be true. Which of the following lists what measuring devices the students need and measurements they should take to collect the necessary data to test the relationship between a torque exerted on the door and the change in angular velocity about the hinge of the door? Justify your selection. You guys have seen plenty of questions like this. You guys know AP likes these kind of questions, right? They're students trying to figure something out. What measuring tools do they need? I have a whole poster for it over there by right by that fume hood. You guys see that yellow looking one? This is common high school measuring tools, right? What tools do you need to measure what things? Right, we got to get torque. We got to get change in angular velocity. So let's bring this over here, sketch this out on paper, I think. Even before we look at the answer choices, I bet we can kind of figure this out. Okay, so let's get a door going. Door. Here's the hinges. Right, here's the doorknob. And, I bet it could be like rotating, right? You go through some angle there. It has some rotational inertia. Here's the radial size of that door, R. I bet we're going to apply some force like F to get a torque, right? Right? Guys, isn't torque equal to R cross F, right? Where we're just multiplying the perpendicular components. If these are already perpendicular, you can just multiply them. If they're not, you got to do something like sine of an angle, right? Right? And we got to figure out there's some resulting angular velocity. Now, the tricky thing is that with this torque, torques cause not angular velocity, but angular acceleration, right? Torque is R cross F, but torque is also I times alpha. What that means is if you apply a constant torque, this is going to be like speeding up rotating. So it's not going to rotate at a constant omega. But the question is, what is omega, right? What's the angular velocity, right? Guys, isn't that like turns per time, theta over t, right? Here's like, do you think you could use maybe a protractor to get what angle it's turned through? But you would also need some kind of stopwatch, right? You know what? I bet at some point we're going to have to make a connection here, right, to all this kinematic stuff. But let's do it. Here's the other formula for torque. Torque equals I times alpha, right? So if you had a meter stick, you could measure R. R, measure with a meter stick. I bet that's going to be one of the measuring tools. Force, I bet you could use a spring scale you could attach to the door and pull, or AP likes force probe, something to do with like measuring a force in newtons, right? Meter stick, force probe, right? Now, this is, we know what rotational inertia is, where they said it was given to you, right? So that could be checked. You could just know that it's a given value. You don't need a measuring tool for that, right? But alpha, right? Well, I bet you'd have to calculate alpha because you have to say, okay, it starts from rest. This is 0. it goes through some angle and some time. Right? Okay. You can make a connection there, right? It goes through some angle and some time. That sounds like, I think this top one actually, right? Omega is 0. Use the protractor to get this, stopwatch to get this. You can calculate alpha. And you can use that now calculated value of alpha to figure out how fast is it rotating at that particular instant, right? So I think theta you could measure with a protractor, and time interval you can measure with a stopwatch. And use these in conjunction with each other to figure out alpha and omega, right? Or yeah, okay, like that. Is that right? Or you guys see like a roadmap of how you would solve this? Okay. But you need 4 measuring tools, I think. Okay, 4 measuring tools. Is it? Right, so let's switch back over here and find which answer choice says those 4 measuring tools. Okay, I've got the version up here now where I can't see exactly how you guys answered, but I like this version because it doesn't give us the green box, so there's no like confirmation bias. We can actually go through and see it for ourselves without our brain honing in on what's there. Oh, of course that would be the answer because it's got the green box. Right? Protractor to measure the angular displacement. Okay, true. And a meter stick to measure the radial size. True. Okay, but we're short a few tools. We can't answer the whole question with just those. A stopwatch to measure the time interval, true. Meter stick to measure the radial distance, true. But again, we're short a few materials. Okay, force probe to measure force, stopwatch time, meter stick to measure distance. Okay, but it doesn't say anything about angle, so there's no way you could really get omega, right? Or I don't know. Okay, stopwatch for time, force probe for the force, protractor for the angular displacement, meter stick for the radial size. Okay. Option D, I think, has all 4 parts that we need. Right? Yeah, answer D. Okay, right, you guys good there? Right. Yeah, so AP loves these questions about like how do you design some experimental procedure, and you have to think, okay, well, I'd have to measure this to get this, I'd have to measure to get that to get that. Okay. It's one of those questions there. All right, next question. So same scenario, we got this door we're opening. Students must determine how to test the relationship between torque and the angular velocity of the door. Okay, so we've been looking at friction is negligible. How should the experiment be conducted to test the relationship between torque and the change in angular velocity in a way that minimizes experimental uncertainty? Right? Minimizes experimental uncertainty. They usually do several trials, right? Like do 3 trials and take an average, or do 5 trials and take an average. Okay, so it's probably going to be in the answer somewhere. Let's check this out. Okay. Options A, B, C, D. Okay. Sometimes spotting similarities and differences for the answers can kind of narrow it down. Students should perform several trials, see applying the same force at the same distance. Hey guys, if you do the same force at the same location over and over and over, that might reduce experimental uncertainty, but you're not going to get a relationship between any 2 variables because there's no independent variable going on. You're just doing the same thing over and over and over. So on a graph, that would just be like a single point. Or if there was a little bit of error in your readings, maybe like a group of points, like a clump, but it's not going to show a relationship between 2 variables, right? Okay, so that can't be true. See, option, and I think option C is wrong for the same reason. Yeah, same force, same horizontal. Yeah, if you're not changing anything, then there's no relationship to test between 2 things, right? We're looking for a horizontal axis, vertical axis. We want to change one variable to see how something else responds, right? Students should perform several trials applying the same force at different vertical distances, or option D, applying the same force at different horizontal distances. Okay? Well, I'll switch back over to this picture that I got drawn up. Check this out. Okay? Guys, if you change the vertical distance, then R cross F isn't like the same radial distance for some force, right? Which is not really changing the torque. So you're not getting any different torque. So again, on a torque versus anything graph, it's just going to show up as like a blob of points again, right? Right? If you push down here in this corner, or on the doorknob, or on the top right corner, radius is the same from the hinges for all those. But if you change the horizontal location, you would be changing this radial distance from the hinges, which would give you different torques, which is going to set up different angular accelerations, which is going to result in different final angular velocities. Right, so that's what we got to have. Right? Back over here. I forget which one said that though. Different. Okay, I think that's option D, right? Yeah, option D. All right, let's confirm. The answer should be D. Hey, D. And one, you guys get that? Right. If you have any questions about these, let me know. You can go back and fill in some. Right. Or so same scenario. We got a door. To create graph of the door's angular acceleration as a function of the net torque. Okay. Now angular acceleration may be something we could calculate. It was like one of those middle calculation steps we were thinking earlier, right? So, okay, how far did it turn? How much time? We could set up some kinematic equation, figure that out. Right? But hey, angular acceleration and torque, right? I can already think of an expression that links those two variables, right? Isn't torque equals I times alpha, right? Oh, and remember, they mentioned before about like being allowed to know what the rotational inertia of the door is, which is the other variable in that expression, right? I, right? But that's the question, right? How can the students analyze the data to determine rotational inertia of the door about its hinges, right? Usually if AP says you're given something, you're not also solving for it, but okay, that's right. So let's bring this over here. Right. They said we're going to graph alpha versus tau. Let's do that. So we're going to put alpha here. It's good. That's angular acceleration. It could be in radians per second squared as a function of different torques. Tau is torque. That could be in, guys, what's the unit? Newton meters for torque, right? So here, we apply like the same force at different horizontal locations. We're getting different torques, right? We're treating that like the independent variable. We're saying, well, how does it accelerate in a rotational sense? That's angular acceleration. I know what this graph is going to look like. This graph is going to look something about like this, right? Where you could do a line of best fit, and it's going to be a straight line. How do I know that? Because I know torque equals I times alpha. Does that look like y equals mx? Right. Except one more thing. It looks like the axes are actually switched. So it's not y equals mx. It's more like this is like x and this is like y. Okay, so maybe I should rearrange this. There you go. Alpha equals 1 over I times the torque, right? Now that looks more like this graph, like y equals mx. If this is your y-axis and this is your x-axis, which they are, boom, boom, right? Then this right here, since this is your slope, right? So the slope of this line is the reciprocal of the rotational inertia of the door. Okay. So if you didn't know the rotational inertia of the door, but you have a bunch of values for torque and angular acceleration, and boom, 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 do it just like that. Okay. So we need the reciprocal of the slope. Okay. You guys got that? Right. So switch back over. So alpha versus tau, we need the reciprocal of the slope to get the rotational inertia of the door. That's what we're looking for. Right. That's angular acceleration as a function of the torque. Okay. Right. We need the reciprocal of the slope, which looks like option B. The inverse of the slope of the best fit line. Okay. Let me confirm the answer is B. Yeah. Okay. You guys good with the answer is B? Right. Now, option A would be like the next best answer. Of course, the answer isn't actually the slope, but if you did figure out the slope, you'd be one step away. You could just take the reciprocal. Right? Or if they switch the premise, what if they said, let's do tau versus alpha? If they switch the axes, then the answer would also be A, right? Okay, let's go. All right, next one, number 4. Okay, so new scenario. It looks like this one has 3 questions. Okay. Ooh, angular acceleration versus time, right? Okay, so some of the first stuff we did in this class was kinematic motion. I think this is going to be a kinematic type question. Okay, so this tells us like the rate that it's speeding up spinning. You can think of it that way. Okay, and guys, what does the area underneath that curve tell you? It's the shape of a rectangle, right? What physical property does that represent? A change in, change in angular velocity, right? Okay, right, that's like delta omega, right? The change in angular velocity, right? I think most of you guys are in calculus. What's the calculus term for what you just did? It starts with an I. Integration. Right, integral. Okay. Now, suppose you make a, let's do that. Let's make the other 2 graphs go along with this, because that's acceleration versus time. That's angular acceleration versus time. Let me bring this over here. Let's break out a new piece of paper. Right, we're going to do 3 graphs right here. 3 graphs, right? Do you guys have your notes out today, right? Because we're doing lots of notes, right? you guys know all these questions. Just like always, I'm not only going over the correct answers, also think about all these other questions they could have asked about this, right? Okay. They gave you angular acceleration versus time. Oh, let me make sure. Let me read the paragraph and make sure they didn't. Something else I want to check for. Let me check. Oh, yeah. You know what? Let me bring my screen back over here because there's a detail in the paragraph that is going to affect the other two graphs. Oh, you guys see where it says initial angular velocity of 3 radians per second clockwise? You guys see that? Right. And somewhere else they say the positive direction is considered to be counterclockwise. Right. So at time 0, it was already rotating. And it was rotating in the negative direction, right? Because clockwise negative, counterclockwise positive. You guys see that? Okay. All right. Right. And let's see if the area under the curve is change in angular velocity. Do you guys see after half a second it'd be turning around? Because guys, what's 6 times 0.5? It's 3, right? Now, if it started at negative 3 radians per second and it changes by positive 3 radians per second, it takes half a second to like start turning around, go back actually counterclockwise. Okay. Right, so let's bring this back over here then. So I've got angular acceleration and radians per second squared as a function of time and seconds. All right, let's do omega versus t. So that could be angular velocity in radians per second as a function of time and seconds. All right, and let's also do theta versus t. It could be in angular displacement, could be in radians. Time is still in seconds. All right. And here, I'll give you guys that point. Right. And also, they told us this alpha right here is just constant. Okay. Right. So go ahead in your notes, draw what do those other two graphs look like. Right. So you know what alpha versus t looks like, it's just constant, which is usually the case for this class. If you ever see a kind of kinematic question that says something about uniform motion, think constant acceleration. Right. Very rarely in this class do you have any motion that's not uniform like that. All right, you're just gonna get these, like all 3 graphs. Gonna get all 3 graphs. All right, Stephen got them. All right, yeah, got them. I think Melissa's got them. All right, so you guys get these, right? You guys get these. Okay. So, said omega versus t. Said it was rotating at 3 radians per second clockwise. Clockwise is negative, just like right there, right? Right. We figured it would take like half a second to bring it all the way to 0 radians per second. Then it would turn faster and faster counterclockwise after that. That's that graph, right? Right. Where the slope of this line is angular acceleration, that coordinate, that slope, that coordinate. Okay. How about theta versus t? That's what shape is this going to be? Parabola. Right? I think it's going to look something about like that, right? Where the maximum angular displacement is going to correspond to it turning around, right? So it spins in the negative direction, and then slows down, and then turns around, starts going positive, and then just picks up after that. Right? Right, there you go. That's 3 graphs, right? Right? You guys can get those? All right, let's switch back over. I forget what they were asking, but it'd be good to know that, right? It'd be good to like see right, the graph they gave you and the premise and be able to put that all together in your head, right? Now, we've got 3 questions, so I guess we're going to answer 3 questions. How can the graph be used to determine the angular speed of the disk after 2 seconds? Ooh, angular speed of the disk. Do you think you could take the area under the curve, which would be a rectangle, for 2 seconds? What would that be? 6 times 2, is that 12 radians per second? No, that's a change in angular velocity. Let's get an answer right here. Because if you started at negative 3 radians per second, and you change by 12 radians per second, because 6 times 2, right? Guys, what is negative 3 plus 12? Is that 9 radians per second? Which is the exact answer to this question. That's how fast it's spinning. right? So let's see which one says that. Determine the area bound from 0 to 2 seconds because this area represents. Option A was so close, so close. That word right there. It's not the final angular velocity. Unless it started from rest, then that would actually be okay. Okay. Let's see, option B. Same. Here we go. Bing. The change in angular velocity. Okay. All right. So you guys see what's got to be option B? Okay. All right. So let's confirm that. Make sure. All right. Questions there? Okay. So we got 2 more questions about this graph looks like. And so same graph. Yep, that's the same scenario. Which of the following graphs qualitatively represents the angular velocity? Okay, from 0 to 2 seconds. Oh, well, you got the answer right in front of you because we just did that in the notes, right? So let's just see which one matches you guys did. All right. Okay. Option A is, well, backwards of what's going on. It's only for like the first half second anyway. Option B says it starts from rest, which no. Option C, gets everything exactly in reverse. And option D, that's the one that matches your notes, right? Okay. So did you get the initial angular velocity right? Did you get the positive direction counterclockwise correct? Okay. Option D. Let's confirm that. Should be option D. Yeah, option D. Option D. You guys good with option D? Okay. All right, one more question about the scenario. What is the angular displacement after 10 seconds? Kind of weird they actually went beyond the graph, but let's just extrapolate. Let's say that it just keeps accelerating at the same rate. It does that for all 10 seconds. 10 seconds. All right. So let's bring this back over here. Okay. I'm just going to go ahead and plug this in a formula. Right. The question is angular displacement. They gave us a time. Does that sound like the first one? First one, we're solving for angular displacement. They gave us the time. Let's just plug everything in and see what happens. Forget what the answer is. Let's see if we get the correct answer though. Right. Which also be the y coordinate on this theta versus t graph. Let's check that. So theta equals omega naught t plus 1/2 alpha t squared. You guys could definitely memorize this, right? Just know the kinematic formulas. You gotta know the kinematic formulas, right? AP physics. Right? So let's go -3 radians per second, doing 10 seconds plus 1/2 6 radians per second squared, which is a constant value straight from the graph. And then we're doing 10 seconds again, it shows up, and then square the time. All right, pop it all in and see what happens. Oh, right, we'll do some mental math here. This is -30 radians plus 10 squared is 100 times 600 divided by 2 is 300. That's radians. Put it all together, it's at 270 radians. Right, 270 radians. Okay. I'm curious, what is 270 divided by 2 pi? Right, that's, by the way, about 43 revolutions. 43 revolutions. You're curious about that. Right, but I bet the answer is going to be 270 radians. Okay. Switch back over here. All right, we're looking for 270 radians. Right, and remember, they did say displacement. Notice they didn't say distance. Because if this was like, if you're like driving around in a car, your odometer would probably add everything up like absolute value. But displacement, we're starting to go into negative territory, and we were in positive territory, and like the net change would be 270 radians. Right? Okay. Right. So C, option C. There we go. Option C. Right, you guys go with option C? All right. All right. Number 7. Look at this. From the picture, you can probably figure out everything's going on. Let's confirm this with this paragraph. Uniform rod at rest on a horizontal surface. Okay, horizontal, so don't even worry about gravity. That's into and out of the page. You don't have to worry about that. Student can launch a sphere of clay in any of those 3 points, X, Y, or Z. Path X and Z are directed, wait, what? Path X and Z are directed toward the center of mass toward the center mass of the rod. Okay, just different angles. Okay. In each case, the sphere is launched with the same linear speed and sticks to the rod. Time of collision is t naught. A pivot point is on the left end. Okay, which probably could have guessed too. All right, So a lot of the stuff in this paragraph you probably could have guessed just by looking at the figure. Right. And right there, I'm already thinking that I made a poster for you guys specifically for a scenario like this. So just bring this over here. I'm talking about this poster right here. Right? I forget what the question is or the questions are. Right? I think it's 3 questions on those, right? But this is the first thing you should be thinking. You're thinking, okay, I see some kind of collision going on. By the way, they said about clay, right? Because if you're talking about clay, we're probably going to talk about a what kind of collision. Inelastic. It should stick to it, right? Right. I think they specify that somewhere too. Right. Right. Here I've got this pivot point up here, and then right. So it's going to get this stick rotating at some rate, right? Maybe omega, how many radians per second, right? And that's how you solve this. You say angular momentum of a point mass, mvr, right? And then you can take that and set that equal to, see, I times omega. I think I got a poster for that too. Where's, well, that's like this I times omega going on here, right? Which will tell you ultimately how fast is it rotating around, right? It's I know I got poster for the ice skaters too. Where's the ice skater? Here's the ice skaters. So I'm thinking like I mean, it's the same expression. I just wanted to remind you guys the same thing, right? Right. So MVR equals I omega. Then you could just solve for omega, right? I think it's the general premise. That's the right, the big picture, what we're looking for, right? Switch back over. Check out this actual question. Okay, friction is negligible. Okay. The sphere clay travels along path Z. Okay, let's check out path Z. Ooh, okay. Guys, what's the radial distance along path Z? Z for 0. I don't think that's going to cause any kind of torque. Some time of that collision, but it doesn't matter, right? And there's 0 angular momentum, right? MVR, R is equal to 0, right? I think it's just it's just not going to move. I think it's what, right? Which of the following correctly predicts the change of any quantities, linear momentum and angular momentum? And this is for the clay rod system, right? Now, if this was a closed system, then there's only one possible answer to this question, which is that any kind of momentum is conserved, right? Linear or angular is conserved, right? So the answer would have to be A for any closed system. The answer is always A for any closed system. But I don't think this is a closed system because this pivot point is like grounded into the earth, right? Right? Like if these were like asteroids floating around in space, that'd be like a different story. But that pivot point is like grounded into the earth, right? So there's like a force from the earth, from the pivot point. So I don't think you can exactly say that momentum is conserved. Linear momentum is going to decrease for this system here, right? Because the clay is in motion, there's some momentum, and then comes to a stop. That's a decrease in terms of linear momentum. So I'm going to start with either C or D. It narrows down to, right? Right. Now, angular momentum. Let's think about that poster I just flashed up. Isn't that MVR from this perspective, right? MVR, right? Which we said was 0 to start with. So it's really 0 minus 0. And 0 minus 0 is just no change. So 0 minus 0 is just 0. So I think I'm going to go with option C. Do you guys like option C? Let's check this out. Option C. Yeah, option C. All right. Ooh, we have another couple of questions about these blobs of clay. Okay, so same scenario looks like. Consider path Y. Okay, so we're launching path Y. Sphere of clay is launched and collides with the rod, distance lowercase l. The length of the rod is capital L. Rotational inertia of the rod is I sub r. And the mass of the sphere of clay is m sub c, mass of the clay. So inertia of the rod, mass of the clay. The sphere of clay is considered to be a point mass. What is the angular speed of the clay rod system after the collision? So angular speed, omega, clay rod system. Where do they say? Oh, sticks, right? I mean, the clay is going to stick. That's why they pick clay to start with. But just want to confirm that. Okay, so we know it's inelastic. Now, here's why that matters. Because if it bounced off like a bouncy ball, boing, then the rod itself would be set into motion with some angular velocity. But that would be it. Right? But if the clay sticks, well, that has some rotational inertia too. In fact, it's not going to rotate as fast, and that would be one of the reasons. Right? because it's adding inertia to the system. Okay. So let's put these ideas together right here. Right. Basically this and then this. Let's combine it. Let's put it all together. All together. Okay, so we got this pivot point right here. Here comes the ball of clay. It's m sub c. It's coming at some velocity, call it v naught. It's gonna stick right there. Right. Now that's at distance lowercase l. Here's lowercase l. Okay. And I said the full length of the rod is capital L. Right. And the rotational inertia of the rod is I sub r. So go ahead and throw that on there too. Right. So how fast is this going to start rotating post collision? That's angular velocity omega. It's going to be right. So let's do conservation of angular momentum. Right. Maybe do sum of angular momentum initial equals sum of angular momentum final. Okay. So it's all provided by this point mass at some radial distance lowercase l. Right. So that's mvl. Right. So mass of the clay, initial velocity of the clay, lowercase l. Isn't that the source of the angular momentum? Right. And when it sticks, then we got okay, I times omega, right? But it's I total. And I total is the sum of both the rod, that's I sub r for the rod. Don't forget the clay stuck to it. So I'm going to say plus. And okay, here's where maybe you actually do have to memorize something that I said you would not have to memorize. Is it down here? Okay, yeah, it's right here. It's right here. Okay, all right. You guys remember this rotational inertia table? Okay, a single point mass is just mr squared, which is exactly the one we need, right? Yeah, in general, you don't have to memorize this stuff, but maybe it's a good idea just to memorize that. Can you guys just memorize that for a point mass to be mr squared? Right? For that matter, the ring is just kind of the same thing. So maybe you can throw that one in the mix too. Right? I mean, the more you know, the better, right? Throw in this one if you're ready for something else. Right? All right, so here it is. Point mass, I got a mr squared, right? Except I'll call it mass clay and then L squared, right? And this is all times some omega that we're solving for, right? So angular momentum is I times omega, and this is like a total I. You guys okay with where all those bits come from? Okay. Who's got any question about where anything comes from? Okay. Notice what I never used. I never used the full length of the rod. You guys see that? Right? I mean, you can kind of make the case that it's already embedded in this capital I. So it does sort of matter, right? For that matter, I guess it'd be this expression right here, right? If you had to like calculate it yourself, right? Right. So we're one algebra step away. All I have to do is take this group stuff and just divide it over, right? So omega equals big old fraction. Got mass of the clay, initial speed, lowercase l, all divided by IR plus MCL squared. Wouldn't that be the answer right there? Okay, right, that's how fast it's going to rotate post collision. Okay. All right, let's bring this back over. There you go. Here. All right, see if we see something like that. Ooh, okay, we got a bunch of answer choices that look kind of similar. Right. I don't like option A because I see capital L, and option B the same thing, which I never use in the calculation. Option C looks exactly like what I just wrote. Right, pretty much, right? And then option D, it looks like they picked the wrong pivot point, right? So I think the answer is C, right? Any question about why the answer would be C? All right, you guys go with C. Right. Oh, and there's another question about these blobs of clay. Let's check this out. Consider the scenario in which 3 identical spheres of clay launched simultaneously. Of course, identical meaning same mass. Right? I think, or they said the same speed also. Right? Along each path, all spheres of clay are launched at same initial linear speed and collide with the rod at the same time. The time of collision is t naught. Which of the following predictions is correct about the motion of the system containing the rod and the 3 spheres of clay immediately after the collision? Right. So what kind of motion setup? Well, maybe clay blob Z, I can just kind of ignore. I mean, it will add inertia to the system, and for that reason, it's not going to spin as fast as if you hadn't thrown clay Z, but it's not going to determine any kind of direction motion, right? Now, clay X and Y is like a battle for direction. Right? Guess which one of these, X or Y, has more angular momentum? Y. Yeah, because it's a greater radial distance from the pivot point. Yeah, so same M, same V, but different radial sizes, right? Or if you like, if you multiply that by the time interval of collision, which might be like a tiny fraction of a second, it would also provide more torque if you like think of it that way, right? So I think Y is going to win over X. Isn't that going to send it clockwise? Clockwise? Let's see if there's an answer that says clockwise. A, I think. Option A says clockwise. Oh, you know what? Option C also says clockwise. Which one is true? Constant angular speed or changing angular speed? What do you guys think? Constant. Yeah, right. Because a couple of reasons together. Horizontal surface means you don't have to think about gravity. Ignore that. And also, there's no frictional loss. Where did it say there was no frictional? Oh, friction is negligible, right? So once it gets in motion, you just for 1,000 years like keep rotating at the same angular speed. So the answer has to be option A. If there's no friction, it just goes at a constant angular speed. Okay, you guys good with option A? Option A. All right, number 10. Ooh, a table. Angular speed as a function of time. Okay, so time's ticking 1 second along, and then angular speed. Hey, guys see the numbers decreasing at a constant rate? Ooh, that means who can tell me, who can look at that table and tell me what is the angular acceleration? What is the angular acceleration? Are you losing 10 radians per second every second? Is that called negative 10 radians per second squared? Yep. Right. I forget what the question is, though. Let's check it out. Table shows angular speed as a function of time. Which graphs could represent, angular position as a function of time? Right. So they went the other way with that. Let's do another one of these sets of graphs. We're going to do all 3 graphs right here. Right. So since you guys got your notes open, here, you guys draw these 3 graphs while I'm drawing these 3 graphs. For that scenario, theta versus t, omega versus t, alpha versus t. So theta in radians versus time in seconds, omega in radians per second versus time in seconds, alpha, angular acceleration, that's radians per second squared, it's a function of time in seconds, right? Remember, like 50, 40, 30, 20, 10, that was omega versus t. So if you graph that, that would look kind of like, well, something like this, right? It will go down at a constant rate. Okay. So that, maybe I might use that in a different color ink, right? To like, just to distinguish it from the axis a little better, right? Okay. So there's, if you take the table and you just plot the points, coordinates, right? You get that graph. Okay. So what does alpha versus t look like? Yeah, straight line, it's negative, right? So that the slope of omega versus t is the coordinate of alpha versus t. It's negative and it's constant, right? Okay. And finally, the tricky one, theta versus t. What does that look like? Here's a hint. What property of omega versus t tells you something about theta versus t? Area, right? And if you're ever not sure, I know there's a bunch of graphs you guys see in this class. So, like, what property, what graph represents what? Look at the units on the axes, because it'll always tell you. Guys, radians per second and seconds. If you divide those two, radians per second, that's called radians per second squared. Okay, that's like rise over run. That means the slope of this is the coordinate of this. Right? But if you multiply those two, what is radians per second multiplied by seconds? Radians, which describes an angular displacement. Area is something to do with base times height. Now, a triangle shape is half of that, but in terms of the units, you multiply it. Okay? It tells you the area under the curve. Let's say I split this into 3 seconds. 1, 2, 3. It takes like 3 seconds for this thing to slow. Well, actually, they said 5, didn't they? I'm just making it in general. I guess 5 seconds, whatever. Right? 5, 6 seconds. Right? Something. So if you look at the first interval time, the next interval time, the third interval time, you guys see the first interval time has a huge area? That means that in terms of angular displacement, it picked up a bunch of angular displacement. But the next interval time, that trapezoid is not as big, which means it's still spinning in the positive direction, just didn't accumulate as much displacement. And that third interval, it's a little tiny triangle. So as it slows to rest, it's still spinning in the positive direction. It's still accumulating angular displacement, but hardly anything. And what shape is this right here? A parabola. And where's the vertex? Is that where my pin is? Yep, there's the vertex right there. Vertex parabola, right? You know what? This has been hanging up from my ceiling the whole time. Ha 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 ha! It's this one right here. Ha ha! Here's the answer. The whole time. This is the same thing. All right, so switch over here. Answer this question then. Angular displacement versus time. Right, so that was that top graph we just did. No. Ooh, that one looks pretty good. Or actually, option C is the only one that even comes close, right? So option C is the only one that kind of checks out. Oh, they only went to 4 seconds too, right? That's why it didn't quite reach the vertex. Right? It's got to be C. Got to be C. Give me a C. Oh yeah, C. All right, you guys good for C? All right. Number 11. Ooh, looks like something rotating clockwise, but is it speeding up or slowing down? Slowing down because the acceleration is opposite. Kind of like a car braking to a stop. Disc fixed to a horizontal axle between two supports. Okay. Friction is not negligible, which makes sense because it's slowing down, so friction could be causing that. Right? At time ts, the disc is rotating about the center with angular speed omega d. Student measures angular displacement delta d, point of the edge of the disc, until the disc no longer rotates. Okay, so slows down to a stop. We're saying like how far did it turn, maybe with the protractor. The angular acceleration is determined to be alpha sub d, and this value remains constant, right? Which is usually true for this class, right? You have uniform motion, constant acceleration, constant rate of slowdown. Based on the data, if possible, how could the student determine angular displacement, point on the edge of the disc, time ts until the disc no longer rotates if the initial angular speed is increased to 2 times the original value? Ooh, justify your selection, right? So let's bring this off straight before we start going through their answer choices, right? Let's think, what is the actual answer to this? How would you get that? Right. Actually, I think these graphs you just drew in your notes could be really good for answering this. Let's focus on this middle one right here. I'm going to blow up that middle one. Blow up the middle one. Omega versus t. That's angular velocity versus time. Right? Now they had some initial value and it slowed to a stop. Right? Then we said we're going to go back and we're going to double that initial value. They got like twice as fast, 2 omega naught. Right? Guys, what does the rest of this graph look like? Does it do zoop, that right there? Right? Hey, is that the exact same angular acceleration? Is that alpha and that alpha the same alpha? I think it is, right? And the question though was something to do with angular displacement. So let's think of this picture up. If the let's break out the pink ink. How about that? Right. The initial angular displacement from the first run was this right here. Here's your theta, your delta theta, right? Okay. Now when you go back and you speed it up to twice the initial speed, how many times further does it actually rotate? 4 times. You guys see 4? 1, 2, 3, 4. That's why I did it in a little triangle. Okay. Well, all right. So that's gonna have to be our pause point. All right. I'll see you guys tomorrow. I was about to bring this guy in, do a little bit more, but yeah, we're gonna have to finish that another day. Another day. Oh, yeah.